weekend. You're well rested, and so you're ready to begin another week of studies. I also want us to carry on from where we left in our previous class. That is, we go on with the root locus sketch, our discussions on the root locus. Allow me to say at this point that I already sent to you guys the notes. I'm sure you already have a copy of the notes, especially on the root locus sketch. So what I will try as much as possible to do, because that saves me time, is to focus on areas that are critical, just to mention a few areas. So I will not go through the notes again. I will not even do the examples that you have in the notes, because you can actually study that on your own. Those notes are self-explanatory, so you can read them and do those examples on your own. What I will, however, do is just mention critical points that I know you need to remember. And then number two, I will also try and do the not the examples, but the exercises that are provided in the notes, the ones without the solutions. So I will try and solve the problems that don't have the solutions in your notes. And it may be any other problems that you may encounter. We'll try and solve those, so that we leave the worked out examples for you to do on your own. Please, I want us to take this seriously, because you know that as soon as we are done with this root locus, I will have to present you guys with a CAT, a continuous assessment test, to see how well you have understood the concepts around the root locus. So in another 2 weeks, we're probably going to have a CAT. So it's important that you try as much as possible to start practicing as many examples as possible on the root locus sketch. I'll communicate the details of that later on, and it's going to be physical. So just to give you a heads up to take your studies seriously as we go along, so that we finish this part. Remember, this is the basic introduction to root locus. We're supposed to go to another stage where we are actually doing design of control systems using the root locus technique. So the design element will come later, once I am satisfied that you've understood most of the concepts around the sketching of a root locus. So allow me to share my screen at this point, so that we continue. Good. Okay, so now I hope you can see my screen. If not, then you'll probably need to notify me. Now, if you remember, what we have done previously is we've used basically some 5 rules, so that we are able to quickly sketch a root locus. Like I told you, because we are doing this manually by hand, we can only achieve a sketch. We cannot actually be able to draw a proper root locus. We can only achieve a sketch. So because we can only achieve a sketch, we need to try as much as possible to make the sketch as accurate and to reflect the real root locus as possible. The only way to do that, in order to improve on our sketch, is to find critical points within our root locus, and to find points that are very necessary, or calculate points that are necessary to sort of provide more information about our root locus sketch. The initial sketches we did, I am not sure if I can get one. Yes, the initial sketches we did, for example, the one that appears on the screen right now, was just a sketch that, okay, in this case we use the asymptotes, but still it does not provide a lot of information. Number one, it does not provide for us the point at which this pulse leaves the real axis, what we were referring to as the breakaway point. It also does not provide for us the point at which it crosses, the root locus crosses the J omega axis, the imaginary axis, what we are referring to as the J omega axis crossings. So we know it crosses the J omega axis, but we don't know the exact point. Neither do we know the gain at which it crosses the j omega axis. So these points are usually very critical to provide a clear picture of your root locus design, so that you know other aspects or components of your root locus that might affect the performance of your system. So it is important for us to determine these points, and that is what we do in the refining stage of the root locus. The initial 5 stages, the initial 5 rules were only giving us a quick sketch, but then the next stage is to find very, very important points within the root locus to make it as accurate or to be represented as accurately as possible. Sorry for scrolling too much. Let me go back to our point. So now we want to define key areas or key elements of the root locus that we need to be able to calculate. Now, these key areas are, like I've already mentioned, the breakaway point. Sometimes it can be the break-in point. So I'll just say breakaway and break-in points. Please note that sometimes a root locus plot can only have maybe just the breakaway point. Sometimes it can only have the break-in points. Sometimes it has both. So if it has both, you have to calculate both breakaway and break-in points. If it is just one, then it's maybe just breakaway or maybe break-in. You will see from your sketch. The other point that we must find, which is also important, is, like I've said, the imaginary axis crossing. Okay? Then the other point is we must know what is the angle of departure. Angle of departure, we usually say, because we are departing from poles, so it is the angle of departure from when we are calculating the angle at which the root locus departs the complex poles as they head towards the zeros. And so we can also have the angle of arrival, but an angle of arrival to the angle of arrival to complex zeros. So again, notice we are only calculating these angles when the poles and zeros are complex in nature. If they are in the real axis, then we don't calculate the angle of arrival or departure. We only do that when the poles are complex in nature. Yes, you see, for example, if this was a pole, this example that we tried to do last time. So let's say there's a pole here and another pole here. So we want to know what is the angle at which it departs. So we are trying to find this angle here, the angle at which it departs. So this is the real axis, this is the j omega axis. So we want to find the angle at which the pole departs, or the complex pole departs the and as it head towards the real axis, or as it heads towards the zero. Okay, so and that also applies to this side, the angle of departure. Okay, now usually we just calculate one angle because these poles are usually conjugate, they are always opposite one another. So when I calculate one angle, then that is the same angle for both of them, because the other one is simply in the opposite direction, but the angle of departure is the same. The same way, if there were zeros on the real axis, then the root locus probably travels to the zeros to terminate at the zeros. Then we would be calculating the angle of arrival, which is the same thing, the angle of arrival to the complex zeros. Again, we only calculate one angle because it reflects the opposite pole, or in this case, the opposite zero, because they are complex conjugate. Remember the symmetry around the imaginary axis. So the root locus is always symmetrical, always symmetrical. So again, those are just points that I need you to remember because they are critical for us in our studies, and we are going to try as much as possible to do those calculations so that you see how it's done. Okay. But over and above that, generally, you're supposed to be able to sketch a root locus without this information that we are listing down here. You should be able to sketch a root locus. Once you have sketched a root locus, then you're able to now determine these points. But the sketch just needs to use the 5 rules, the ones that don't require you to do any calculations, except maybe when you want to draw an asymptote. But the first 5 rules should be able to help you to draw a root locus plot without, or to sketch in this case, without having to calculate anything. But these ones require calculations. Breakaway and break-in points require you to do calculations, J omega axis calculations, and of course the angle of departure and arrival also require you to do certain calculations. So those are very, very important points to remember. Now, I'm going to do an example again. The examples that are done or provided for in your notes, please read them. I will not look at them. I will only do those ones that are not in your notes. Now, I only want to show you, because again, that information is self-explanatory in your notes. You have information in your notes that show you how to calculate each of these points. So for example, let's start with the breakaway point. And this is for illustration purposes only, but I expect that you read your notes. If you don't understand, then you can always ask. So breakaway or even break-in points. How do you calculate this? Okay. Now, I'm just giving a sketch. If you have a root locus that looks like this, just a typical sketch, guys, don't, let's not, let me just, so let's say our root locus looks like this. So that therefore means, okay, so I'll have to say, let's say it's because we have all there. So then we have a 0 here and a 0 here. So we have a root locus here. You can see that we usually say the root locus begins from the poles. So it's like that, and terminates at zeros. Okay. So now we clearly know that there's a point at which the root locus will leave the poles as it goes to the or as the root locus, or as the poles go to the imaginary axis. Now, those points are usually, now that's what we refer to as the breakaway point. This is the breakaway. Now, the point at which the poles, because the poles, you can imagine, as the gain increases, it is assumed that these poles are moving. So they're moving along the root locus. So they're moving as they head towards, as the gain continues increasing, up to the point where they terminate or end at a 0. Now, in this case also, the point at which they rejoin, that becomes the break-in point, the point at which they rejoin the real axis. Now, what I want you to remember is this. Because these poles are moving on the complex plane, we refer to the poles as complex in nature. So we represent them using S. That's why we say S is equal to -2, or in this case, let's say this is -2, this is -3. So we say S is -2 and S equals to -3. Okay? But when the poles return, or once they are on the real axis, our S is now real. So it is no longer, because we know that S equals to the real part plus the imaginary part. But if the poles only exist on the real axis, then S equals to sigma, or it's real. Okay? So how can we determine this point and this point? So those are the breakaway and break-in points. So what we have to remember, that on the real axis, our S is basically sigma, because the J omega, the imaginary part, is 0. Okay, so now there are about 3 ways in which we can determine the J omega axis. The breakaway and break-in points, and you need to do this. You can choose whichever method you want to use. The first method is actually known as maximize and minimize the gain. The second method, which is my favorite, is the transition method. Transition method. And the third one is using a software or MATLAB, for example. Now, please read about these methods, okay? I personally prefer using transition method, but we can use any method that you want. Now, just quickly mention what how the first method is. Typically, from our rule, remember the angle and magnitude condition emanates from our rule for the root locus, remember, equals to -1. Very important rule, okay? So because we already have this is basically the open loop gain. This part is the open loop, the open loop system that you're provided with. So in our case here, let's assume that equals to some, let's say the S minus 1, S minus 3 over S plus 2, S plus 3, something like that. I'm just giving an arbitrary value. So because this should be equal to -1, one way of determining the breakaway and break-in points is we know that on the real axis, because the breakaway and the break-in points occur on the real axis. So it's a point on the real axis where the poles depart, or it's a point on the real axis where the poles rejoin. Okay, so at that point, S is equals to sigma. So therefore, we can represent this information differently and say K sigma -1, because S is now real over to be equal to -1. Okay. Now, usually, because you can now make K the subject of the formula, so K becomes we are making K the subject of the formula. So I think it's like cross multiplying. And of course, there's a negative here, because if I take this on the other side, and then this comes down. Okay, something like that. So usually what we are referring to, the maximizing or minimizing, is to do that, to differentiate K with respect to sigma. Okay, so you're differentiating K with respect to sigma. So of course you will have to you'll have to open the brackets here. Okay, then you factorize K and then you equate to 0. So once you minimize, that means you differentiate with respect to sigma, and then you set that derivative to 0. Then you'll obtain those points. In this case, you'll obtain 2 points, the breakaway and the break-in points. And from your observation, you will tell which one is the breakaway and which one is the break-in. Because clearly you can see that the breakaway point is on the negative side. The break-in point in our case here is on the positive side. So it means if I differentiate and equate to 0 and solve, I'll find one negative value and another positive value. So the positive value will be the break-in point, and the negative value with the breakaway point. We'll do an example with that. So basically what we are saying is one method to obtain the breakaway and break-in points is to obtain the value of K, and then you differentiate K with respect to sigma. And remember, we derive that from the initial question here. I mean, the initial rule. So the other method of doing this is the transition method. Okay. Remember, I'm going to do an example that is not on your notes. So I need to quickly finish this so that I do that method. So the transition method is simply stating that if I want to obtain the real and imaginary, the breakaway and the break-in points, then all I have to do is obtain the sum of zero. Let me just call this the sum. You sum up all zeros. Okay, so sigma plus zi should be equal to summation for all poles 1 over sigma plus pi, where zi is the negative of zeros. This is negative, very important, negative of zero values. And pi is the negative of all values. What we mean by that is this. Let's say we have poles in our root locus. The poles are maybe s equals to minus 2 and s equals to minus 3. The zeros, s equals to, sorry, what am I doing? S equals to S equals to 4, S equals to 3. I'm just giving arbitrary values. So what we are saying here is we have to take all the poles, like in this case, we have that, the finite poles. We are only summing up the finite, not the infinite ones. So let's start with the zeros. So if you start with the zeros, let's say 1 is at 4, 1 is at 3. So we have to sum the negatives. So what you're going to have is 1 over sigma. Let's start with the first one, is 3. So the negative of 3 is minus 3. So you put that minus 3. Then you add the other 0, which is, here it is at 4. So we consider the negative, which is minus 4. So we'll be having 1 over sigma minus 4. Then you equate to the same thing, but now for poles. So for poles, we're going to have 1 over, the first one is at minus 2. So the negative of that is 2. So I'll be having sigma plus 2 plus. The other one is at minus 3. So I take the negative of that, which is plus 3. So like this. Then you solve. Because now this is, you can actually linearize this equation, and then you solve it using the normal knowledge on quadratic equations and stuff like that. Then you find your values for the break in and breakaway point. Again, we'll get to the point where we do an example using this. More details are provided for in your notes with examples, worked out examples. So I expect that you will read and understand those parts. Now, the other point, so we've shown how to calculate this. We now need to know how to calculate the J omega axis crossing. Now, to calculate the J omega axis crossing, usually it is this point we are looking for, the point at which the poles cross the J omega axis in their pursuit to join a 0 somewhere. Okay, so this is the J omega axis crossing, and it is associated with a certain gain. So we need to determine in is. Okay, so we need to know what the crossing is and what the gain is. Now, I will explain this, but you need to pay a lot of attention to how this is done. Whenever we are calculating the J omega axis crossing, we normally use the root Howey's table. So we have to come up with the root Howey's table. But again, we also have to use the characteristic equation. We have to use the characteristic equation. We have to use the characteristic equation for the closed loop, not open loop. Closed loop transfer function, not open loop. So this is the only point on the root locus study where we need the transfer function of the closed loop system. We have been using the open loop system, but whenever we want the J omega axis crossing, then we have to, because we need the characteristic polynomial. That characteristic polynomial is obtained from is a denominator actually of our closed loop transfer function. So it's very, very important that we do that. So for example, in your notes, we are going to do a typical example, but in your notes, there is one. So let me say, if you have an arbitrary, let's say this is just a transfer function, s plus 1 over s to power 3 plus 8s squared. These are typical, just arbitrary one. I'm not even sure if it works, but I'm only giving you an illustration. We'll do a proper one, plus 11s. No, actually, let me make it more interesting. 11 plus k is plus 8k. So this, let's say you've obtained your characteristic or the transfer function, the closed loop transfer function is like on your screen, but you want to now, one, find the J omega axis, but also two, find the gain of that system at that point, at the J omega axis crossing. Now, to do that, one, we need to figure out from the root table. So how do you draw the root table? This you did when you're determining stability, the root Howey's criterion. So for the root table, you remember, we know that the highest power of s here is 3. So we start from s to power 3, s to power 2, s to power 1, and s to power 0. I'm not doing this, I'm just illustrating. I'll do a proper one when we are doing a good example. Then, of course, you have to write the coefficients of each. So the coefficient of s to power 3 is 1. Then you skip the next one, you go to the second one. So the coefficient of s is 11 plus k. So you have to put it like that. Then you skip the next one. So the other one is just 0. Then you go to the coefficient of s squared, you write 8. You skip, you'll have 8k. And of course, there's nothing there. You can write 0 or you can just leave it like that. It's no problem. Then the coefficient of s. So I've written 1, this, okay? Then the other one was 8 squared, and then this. So now this one is obtained. So for me to obtain this point here, for me to obtain whatever value is here, how do you obtain that value? That value is obtained by first putting a negative. That is what the rule says. Then number 2, you now have to, it has to be a negative of the entire thing. So you have to multiply, like the way we were getting determinant. So it's multiply, you cross multiply this. So you'll be having 8k minus, again, the cross multiplication of this, 11 plus k, divide by the point that is right above right above the point you want to determine, and that is 8. So you put that value here. That value will fall here. So you do that even for this, okay? So we do all of that. So you just come up with the table. So once you come up with the table, I'll do a proper example for you in the next hour. So don't worry. So once you come up with this point, Then now, how do we determine the J omega axis crossing, and how do we determine the gain associated with that crossing? Okay, so the rule is, if you have a complete row of zeros, that is what will give you a possibility of an imaginary axis root. So if you have, for any positive value of gain, because remember our gain is from 0 to infinity, so our gain should actually be positive. So for any positive value of gain, you are looking for a row here, either this row or the next row, or even this row, or even the last row. So you're looking for a row that is possibly all the values of that row can go to 0. So for example, if you look at the first row that is associated with s to power 3, you cannot have all the rows going to 0, because already there's a point here which is 1. And then for any value of k, positive value of k, this cannot go to 0, because even if k was 0, then the value would be 11, which is positive still. So this row cannot go to 0. The second row also that is associated with s to power 2 or s raised to power 2 also cannot go to 0, because you already have an element here that is 8. Okay, then the third row is this value here. So you'll check if this value goes to 0. Now, typically, a value that has a fraction like this, a value that is improper like this, is typically able to go to 0, because it's already improper. And you know, if you divide, let's say, if you had a value like this, and then you are able to have k go to 0, then the value will, and because the denominator is a whole number, then the value can go to 0. So typically, the row that goes to 0 is the row with the fraction. It's just natural to see that. Okay, it's the one that you're able to manipulate for everything to go to 0. So that row is the value that you pick. So the row that goes to 0 is the row that you take and equate to 0. So like in this case, I would take 8k minus 8 into 11 plus k. Remember, this is just an arbitrary value, is equal to 0. Then you solve for k. When you solve for k, the value you obtain becomes your gain. The value you obtain becomes your gain. Okay, again, I'm going to do an example for you, so don't you worry. Then number 2, plus you also have another example in your notes that you can look at. Now, number 2, how then do we determine the J omega axis crossing? Because we've just determined the gain by taking the row that cannot go to 0, that can go to 0, the row that can go to 0, and we've equated it to 0, we've obtained the value of k. But how can we determine the J omega axis crossing itself? Very simple. The rule says, in our case, the row that goes to 0 is s to power 1. So you are asked, if you want to determine the J omega axis crossing, you have to look at all rows that are above S1. The immediate row that is above S1 that is even. You see, we would say this is an odd row because of that power there. This is an even row because of that power. This other one is an odd row because of that power. So the rule says that for you to obtain the J omega axis crossing, you have to look at, number 1, the row above the value that you obtained k at. So we obtained k at we call it the s to power 1 row. This is what gave us the value of k. So we have to look at an even row that is above s to power 1. And the only even row above s to power 1 is the s to power 2 row. So the s to power 2 row is the one that should give us the J omega axis crossing. How does it do that? You come and take the polynomial of the entire row. So you can actually see, let me remove all this junk stuff that's confusing you. You can see that this row here, the s to power 2 row, if you have to write it out as a polynomial, you know that the 8 is corresponding to s squared. The 8k is responding to s to power 0 because, again, this is s squared, then you skip s to power 1, so this is s to power 0. So you'll have the row as 8s squared, and then, of course, you skip s to power 1, so we'll have 8k, because s to power 0 is just 1, plus 8k. Then you equate that to 0. But k, you've already obtained from the previous equation. So you can obtain the value of s, and you can see that s is going to be a square root, and a square root is plus or minus any value that you find. So this plus or minus, so this square root is your j omega axis crossing. Because remember, s is equals to sigma plus j omega. But the j omega axis crossing is on the imaginary axis, and it is happening at the origin, the point on the imaginary axis. So it is happening here. It is happening here where sigma is 0. Okay? It's happening on either side where sigma is 0. So if sigma is 0, it means s is equals to j omega. So the value of s that we obtain is going to be a plus or minus j of something, so that we cater for this as the positive j something and this as the minus j something. So that becomes your j omega axis crossing. Again, I am going to do an example for you, of course, and assuming that you will also have done the example on the notes. Lastly, I want to again show you how to obtain these angles here. The j omega, the angle of departure. So this is fine. We'll do an example there. So these two are usually done the same way. Whether you're finding the angle of departure or the angle of arrival, you do it exactly the same way. So how do you obtain those angles? This is usually the simplest one, because all you have to do, let's say you have plotted your root locus and you want to know, so let's say your root locus is like this. And this is just, again, another sketch. So let's say a pole was here, another pole was here, maybe some zeros were here, zeros were here. So let's say your root locus is like this. Okay. Let me say even the other 0 is at infinity. If the other 0 is at infinity. So let's say this is just a typical plot. Let me say the other 0. Let me make it interesting. So this 0 here, let me move it. Sorry. So let me put the 0 somewhere. I want to use a typical value. So let's say a 0 is at this point. That's a 0. The other one is at infinity. So the angles that we are referring to are in this case, we have complex poles. So we can't find the angles of arrival. We look at the angles of departure, because for the poles, we depart the poles as we arrive at the zeros. So, and since the 0 is on the real axis, we don't determine the angles. The angles are only determined if either the poles are imaginary or complex in this case, or the zeros are also imaginary. They are also complex in nature. So what we are trying to find is this angle here, the angle at which these poles depart. And the angle, because this is a conjugate pole, the angle is the same. It's only that it is happening in the opposite quadrant. So it is exactly the same angle, only that in the opposite direction. So we only have to determine one angle. So how do we determine this? We determine the angle using the rule that all the angles, if you sum up all the angles of the poles and zeros on the root locus, they should add up to 180 degrees, or an odd multiple of 180 degrees. This is what I mean. If, let's say, we want to determine the angle of departure, so you only need to determine for one pole and then it applies to the other pole. So let's determine the angle of departure on that pole. So the only way to do it, like we were doing previously, is to subtend an angle from this point. So this becomes like our test point. So you have to draw a line from this point to the other pole, then from this point to the other finite pole. The other, I mean, to this zero. The other zero is at infinity, so you forget about it. So what we want is, once you have subtended an angle, so we are looking for this angle. So let's call this theta 1. Then we call this, and you know very well, this angle is just going to be 90 degrees, but let's call it theta 2 because it's a conjugate. It's directly opposite the other one. And then you have theta 3. We are only dealing with finite poles and zeros. So here, remember the rule was all pole angles are subtracted. All zero angles are added because the poles are in the denominator and the zeros are in the numerator. So all zero angles, you sum them up. All pole angles, you subtract them. So in this case, we could say that big theta 1 is a pole, so minus theta 1, and it's the one we want to find its value. Theta 2 is also a pole, so minus theta 2. Theta 3 is a 0, so plus theta 3 should give me the minimum angle is 180 degrees. Now, clearly, you can see that this angle is going to be 90 degrees, theta 2. And the theta 3, you can determine it because it's going to be the inverse tangent of the opposite over adjacent, and I'm sure you can get those values if provided. Then therefore that leaves you with theta 1, which you can then determine. So once you have theta 1, that becomes the angle of departure of the complex poles. Okay, and if these poles were zeros, you'd still do it exactly the same way as I've done it. Remember, pole angles are subtracted, zero angles are added. That is all there is to this. Okay, so the best way to illustrate this point again is to give you an example. So that's what I want to do. I want to take time and explain the next example for you as much as I can, and then we call it a day. So please pay attention because it's the only example I'm going to do, assuming that you will also do the other, you'll do the other examples that are in your notes. So let's do an example to solve all these things, because these are typical exam questions, because it has so many things that need to be obtained. Example. So please see how you to approach this question and how I expect you to solve it. So a typical exam question would be, given a unity feedback system that has the forward transfer function G of S equals to K into S plus 2 over S squared minus 4S plus 13. Do the following. Number 1, sketch the root locus. Number 2, find the break-in point. This is specified. Find the break-in point. Okay. Number 3, find the J omega axis crossing. Okay. Number 4, find the angles of departure from complex poles. Number 5. This is like a 10-mark question, so it is long. Find the range of gain K within which the system is stable. Yeah, this is between 10 to 12 marks. So very good question. Sometimes because these are 5 points, this can even go to 20 marks. Okay. So these are an entire question on its own because of the many points. 1, 2, there are 5 points. So averagely 3 to 4 marks. Yes, this between 12 to 20 marks. So how do you solve this problem? Having had your knowledge on root locus, you should be able to at least solve this problem and solve it as quickly as you can. So my work here is to guide you through how I expect this question to be approached. Number 1, you're given a unity feedback system. Number 2, we can sketch the root locus. But before we do that, we need to know usually, so solution. So solution is usually identify, so I'm not going to write, so I'm just going to do it. We need to know what are the zeros, and we also need to know the poles. So you can see from our equation that we have one finite zero at -2. So we have one finite zero, and that finite zero is at -2. Okay, that is 1. Number 2, you can see from this equation, because this is a second order equation, we have 2 poles, 2 finite poles because of second order, meaning there are 2 roots. This equation has 2 roots, and so it is 2 finite poles. 2 finite poles, but these poles are complex. So 2 finite complex poles. So how do we find those 2 finite complex poles? Is to use your skill to find the roots of this equation. So the roots of this equation is K into S plus 2 over, so what is the roots of the, so you use your calculator or whatever your skills are in maths to find for to get the roots of this equation, which is S minus 2 plus 3j. Let me call it 3j. So, okay, I want to maintain some consistency here. So plus j3. And then you have S minus 2 minus j3. Okay, so the complex poles are S equals to 2 plus j3 and S equals to 2 minus j3, because they are conjugate. They are complex conjugate. Okay, so that becomes, so now note again, we have 2 finite poles and 1 finite zero. The first question is we need to sketch the root locus. Sketching, meaning we just use the first 5 rules. We don't need to calculate anything. We just need the first 5 rules. So here is a sketch. Sigma j omega. This we have at -2. So we have at -2, we have a 0. So let's say this is -1, -2, 1, 2, 3. Let's say this is -3. So at -2, it's a 0. It's not a -2, we have a 0. Then let's say this is the point, this is the J3, and of course you have -J3. So we have a 0 at 2 plus J3. So there's a pole here and another conjugate pole there, like that. Now, we can determine the points on the root locus, the points on the real axis where the root locus occurs. I think it was rule number 2. We need to know, rule number 2 or 3, what points on the, where does the root locus occur on the real axis? Because we have imaginary poles here, so those ones we can't determine now. But on the real axis, we only have 1, 0 here. So it means 1 being an odd number, to the left of that 1 should be a root locus. So there should be a root locus on this line. And because this is a 0, ultimately something must terminate. So the arrow is entering the 0. Because it's a 0, it means a pole must ultimately come and terminate at this 0. We don't know which pole it is. The other thing to remember, because we have 2 finite poles and we only have 1 finite 0, we should have another 1 infinite 0. So that we assume that the pole, meaning S, this is infinite, S equals to infinity. So because we have 2 finite poles, we know from our previous classes that each pole must terminate at a 0. So if there are 2 poles, we need 2 zeros. So in this case, we have 1 finite 0. So the other one is assumed to be at infinity. So one of these 2 poles will come and terminate at this 0. The other will have to go to the 0 that exists at infinity. The beauty of knowing where that 0 is at infinity is that the root locus here, we have been told, occurs on the real axis here. There's a root locus here, meaning the other 0 that exists at infinity, it's at infinity, but along this real axis. Now, the other thing that we should know is that the poles always travel symmetrically around the imaginary axis, but they are also conjugate. So usually they don't travel in a straight line. They travel in an arc. They move along an arc that is symmetrical about the J omega axis. They only travel in a straight line once they are on the real axis. So what I mean is this: if you have 2 poles like this and they're moving, if this guy moves like that, the other one moves exactly in the opposite manner, but they are conjugate, so they're moving together and they're moving symmetrically. You can see that. So if they're moving like that, like that. So if they're joining like this. So if you look at our question here, notice there is J omega axis crossing involved, there is break-in point involved. That is a clue that there's got to be a point where our poles must rejoin the real axis, but they will have to cross the J omega axis, because notice our poles are on the right half plane, but our zeros are on the left half plane. So it means our poles will have to travel. They have to travel as they move towards the, so they move. And it's a sketch. And join. The same thing happens on the other side. They move and join. So essentially, you will be having a movement like that. And the other one is also moving. Notice they have crossed the J omega axis crossing. So you have a pole here and you have a pole here. As you continue, notice where they begin, K is 0. Where they begin, K is 0. As they keep moving, K increases towards infinity. So once they get to this point, this is our break-in point. We'll need to determine it because they have rejoined the real axis. We'll need to determine that point. But what is also significant is as soon as it terminates, here K is infinity. And even the other pole, as soon as it terminates, K will be infinity. So what happens is one of these poles will move and join this 0 on the real axis, the one at -2. The other one will also move, but will have to go towards the one at infinity. That is where it will terminate. So the typical sketch ends here. We don't know the J omega axis crossing point. We don't know. We don't have this point yet. Okay? This point, we don't know what that J omega point is going to be. Let me just make it a little clearer here. So this is J omega, but we still don't know what this point here is. We'll need to determine those points. We'll also need to determine this break-in point. Then we'll need to determine what angle, at what angle do these poles depart, at what angle. So the angle of departure from the complex poles. This gains was just an illustration, so I don't want to clutter this so much. So we can leave the sketch at that point for now. Notice I have used the skill of knowing where the root locus occurs on the real axis. I've also used the skill of looking at the question and seeing that because they are asking for the J omega axis crossing, it means these poles will have to cross the J omega axis at one point. Where they heading towards the zeros that occur on the left half plane. One is at -2, the other one is at infinity. And as they move in a conjugate manner, and they're all symmetrical around the imaginary axis. Okay? The way you know this stuff is the more you draw root locus, is the more you become very conversant. You can tell the direction of the root locus just by looking at the location of the poles and the location of the zeros. Once you have that, it is very easy for you to know how to sketch the root locus. Remember, it is a sketch. So now, let's move on. So this is the first question, the sketch. So let's look at what the second question asks. Yes, ask. All right. Okay, that's a good question. And the answer is very simple. That rule number 3 that you have read, if you read it again, just read rule number 3 again, as you just read it to me. Read it, but now we're going to read it with understanding. Mm-hmm. Good. Wait. Exists on an odd number of real axis pole. Is it, of course it's finite and closed loop, whichever, but it exists only on the real axis. In fact, that rule, if you read its title, it's the root locus on the real axis, knowing where the root locus occurs on the real axis, not the imaginary axis. We cannot assume that we can quickly determine the direction of the root locus on the imaginary axis. We can only know on the real axis That rule applies only, and you will always see that whenever I'm doing the root locus, it's the one that I begin with so that I know the points on the real axis where the root locus occurs. So it is a rule for the real axis. It does not apply for the imaginary axis. So we cannot say that, okay, the poles that we have here are the rightmost poles. So to the left of those poles, no. That rule applies if those poles and the zeros are on the real axis. If they're not on the real axis, don't apply that rule. That's why it says that the odd number of real axis, finite poles or zeros. So the root locus will occur to the left of an odd number of real axis pole or an odd number of real axis zero. So it has to be real, not complex, not imaginary. Okay? So please use that rule only for the real axis segments. That's why the title of that rule is real axis segments. It is how to know the point on the real axis where the root locus occurs. And you only use real axis poles or real axis zeros to know that point. That's why when I began, I only looked at the real axis and said we only have 1 0, and that 0 is at -2. And because that 0 is at -2, then because it's the first 0 that I have on the real axis, to the left of that 0, there should be a root locus. And I ignored the locations of the poles because those ones are complex. But that rule applies only for the real axis zeros and poles. I hope that is clear. Good. Thank you for that question. Yes, another question?
Yeah, when counting, for example, in this example, when counting the number of root loci, do we say they are the one from each pole, and 2 the one going to the right from the breaking and the one going to the left, or does it count as 1?
Oh, so you are considering rule number 1, the number of branches?
Yeah.
Okay, good. That's another good question. Now, the number of branches is, remember, we define a branch as a path that one pole traverses. So each pole has its branch or has its own path. The path for each pole is known as a branch. So if you want to know the number of branches, it's usually the number of poles. So in our case here, you can see we have how many poles? 2 poles. So typically, you're going to have 2 branches. Now, the best way to illustrate this, and please take note, thank you for this question and for reminding me. Take note, if you want to have a visual, because here we are drawing it manually, ladies and gentlemen, and sometimes we don't have the luxury of having different colors and stuff. I'm just glad that we are doing this online so I can use different colors, but if I were in class, it would be difficult. So please take note. I want you to go and plot this in MATLAB. I'm going to give you even the code to type. It's just 2 lines of code. And then see the plot that has been given by the MATLAB, because MATLAB is giving you a plot, not a sketch. It's a true reflection of the root locus, but it's going to look like this, or like what we have drawn, only more accurate. But you're going to see that it is drawing each branch in a different color. So you can tell how many branches you have by the number of colors that MATLAB has used to plot the root locus. But typically, to answer your question, we are going to have, because we have 2 poles, and each one of them is terminating at their own 0, the complete path followed by a pole is known as a branch. So for example, we would say that one branch of the, let me try and use a different color to just illustrate. So let's say this pole is moving like that. Okay, it's moving like that. And let's say it's the one that comes and terminates at this 0. Now that is one branch. So the branch does not end at the real axis. It ends when the pole terminates. That is one branch. So the other one also moves in that direction. But because there's already, the other pole has already taken the 0 at -2, this one will now have to move to the 0 at infinity. So when it gets to that 0 at infinity, that is another branch. So we have, this is branch 1. So the branch is a complete path. And then this is branch 2. So you will see that MATLAB will probably draw this in blue, and then the other one, it will draw in green. So you can see the path of each pole. And so the path traversed by each pole is a branch in itself. So there are 2 branches here. That is the rule. I hope that is clear. Now,
Yes.
Please take note. Yes, that's okay.
Yes, thank you.
Oh, good. Now, take note. Because at this point, I'm not going to, I know you guys encounter, right now, I'm sure all of you must be encountering you use MATLAB or even Python. I don't have the code for Python here, but I can, because I've used MATLAB a lot. I think I can give you the code. So let's say, if for those who are going to try this on MATLAB, so that you can actually see how the plot is done. So let me draw that code for you here right now. So you can go and do it, and then you will see what happens. Now, because the question is, I think it is, yes, ks plus 2. So we know that g of s equals to k into s plus 2 over s squared. Is it plus? No, it's minus 4s. S squared minus 4s plus 13. So this is the code. First, in root locus, forget about the k. Okay, that's a gain, and it's the one we are varying from 0 to infinity. MATLAB already knows that the gain is varied from 0 to infinity, so you don't have to tell it what the gain is. It has been inherently programmed to know that the gain is varying from 0 to infinity. So we won't have to define it. We only have to define the transfer function, and then it will draw for us the root locus. So let's say you can maybe say numerator equals to, so numerator here is a variable. You can even say A is equals to or B is equals to. I'm only using it to sort of, we can relate to know that it's a numerator. So it's a variable. It's considered a variable. It's not a string. So the numerator equals to, you write it in matrix form. So 1, 2. And then, of course, you terminate it so that it doesn't give immediate results. Okay? Or there has to be a comma here for MATLAB. You have to put a comma there. So it knows, this is how the MATLAB knows clearly. It defines this as, because you see we have s plus 2. So this is s to power 0. Of course, and now this is a sorry, this is s to power 1, and this is s to power 0. So if you put it, he knows that the coefficient of s to power 1 is 1, and the coefficient of s to power 0, which is a constant, is 2. So that is how you define the numerator. For the denominator, we have 1 minus 4 and 13. So you just write 1, comma, minus 4, comma, 13. If you tell MATLAB this, of course, you terminate it there with a semicolon. If you terminate it there, so it knows that this is the coefficient of s squared, it knows this is the coefficient of s to power 1, and this is the coefficient of s to power 0. So it knows that automatically. So that is how you define it. So therefore, our transfer function is g equals to, not g of s. Don't write g of s because you have not defined what s is. So just g equals to, in MATLAB, if you want to get the transfer function, you just say tf. And the tf, you take the numerator and the denominator like that. And you use those parentheses. So you can even, as soon as you enter this, it will give you the transfer function. You'll see the output would be g into k into s plus 1. Not k. K is not even defined. So it will not even put k. It will just put s plus 1 over s squared minus 4s plus 13. So you can confirm that by inputting this code. So once you have input this code, then you're done. You simply tell it to plot the root locus. How do you do that? You just say R locus, and then what is the root locus you want to plot for G, like that, and you press enter. It will give you the root locus plot for this, and you will see that there are different colors for each branch. And because we have 2 poles here, you will only see 2 branches in different colors. But it is a very accurate plot. It is not a sketch. Now, the beauty of this, and this is why I encourage you to be able to write this MATLAB code for different transfer functions so that you see their MATLAB plots, is because when you're doing your calculations or when you're doing your own revisions later and you find a question and you want to sketch its root locus, you can always test yourself and see, let me try and sketch, and then I enter it into MATLAB and see if I obtain the same results as MATLAB. Then number 2, you solve for different. So let's say I've given you a question. Go and solve it. Find you are calculating asymptotes. You are calculating the centroid. You are looking for maybe breakaway point and breaking point. Calculate those things, and then you can check your answers with MATLAB. So what happens with MATLAB is, if I come and bring the cursor and click the cursor at this point, it will give you every detail about this point. You will know the break-in point because it will tell you the break-in point there. It will even tell you the gain at that point. If I come and put the cursor here and click on this point here, it will tell you the coordinates of this point. So you will know, because if it tells you the coordinate of this point, it's going to say S is equals to 4 minus 8J or whatever. Then you know that the J omega crossing is 8 plus 8. So you know the J omega crossing is 8, so that this other one is minus 8. Okay? So, and again, it will tell you the value of gain at that point. It will even tell you the frequency at that point. It will tell you the overshoot at that point. So MATLAB will give you a holistic view of each point. That you can even click a point on the root locus here. It will give you every detail about that point, every detail that you need to know. So that helps you know where the J omega axis crossing is, where what it will not give you are the angles. The angles will not be provided, but everything else, all other information, the J omega axis crossing, the breakaway points, the centroids or the real axis intercept and all that. Remember, MATLAB does not plot asymptotes. Asymptotes are for human beings who cannot predict the location of the poles and zeros at infinity. MATLAB already knows inherently, so it will not draw the intercept lines, okay? Now, I expect that each time I give you a question to go and solve, you'll be able to plot that and check the results with MATLAB. So MATLAB would be like your way of knowing whether your calculations are correct or not. So if you calculate a breakaway point, go and check in MATLAB whether it's exactly the same value. If you want to calculate the J omega axis crossing, same, okay? So this is the code for MATLAB. Good, I beg to continue because we still have a long way to go and we have just less than probably 30 or so minutes. Good, so now the next part is to obtain the break-in point. We are looking for this point, the point at which the poles rejoin the real axis. What point is that? And for me, I am going to use so let me just put breakaway point. No, it's not a breakaway, it's a break-in point. I'm going to use the transition method, okay? You can use the dk over the sigma and you equate to 0. An example is provided in your notes, but I'm going to use this because I find this easier for me to use. I'm not restricting you to this. You can use whichever method you want. I'm just trying to avoid differentiation, maximizing and minimizing. Oh, this is P. Both methods are provided for in your notes, okay? What you have to remember with this transition method is that this Zi and this Pi, of course, Z stands for poles and Z stands for zeros and P stands for poles, but the negative values, they are negative values. So like, for example, we have our pole as, we have our zero as S, so 0 was S equals to -2. Our pole was S equals to 2 plus J3, and S equals to 2 minus J3. So we have to get the negative of these values. Okay, so let's start with the zeros. We only have one finite zero, so we are going to have 1 over sigma. Now the 0 is at -2, so the negative of that is +2. So I simply put +2, the negative of that 0 location. Okay, so that's it, because we don't have any other 0. The other one is at infinity, equals to, now let's sum up the poles. Again, it's going to be 1 over sigma. Let's look at the first pole. You get the negative of this value, so it's simply going to be -2 minus J3. Okay, plus 1 over, get the negative of the second pole, which is going to be sigma -2 plus J3. You're basically finding the negatives, like what is negative S? What is negative S? Okay. So once you have this, then you can now solve it. And some of the calculators you have can already solve this easily. Okay. Now, I don't want to spend time in maths. You can see how to solve this. Okay. Basically, you're going to have 1 over sigma plus 2 minus 1 over sigma minus 2 minus J3 minus 1 over sigma minus 2 plus J3 equals to 0. So you can have your least common multiple, I don't know, factorize, do whatever it is you want, put them in your calculator and solve for sigma. Okay, because sigma is the unknown. Okay, so if you solve this for sigma, for me, I can enter it quickly on Symbol Lab or on Wolfram, and I get the solution. Okay, just a minute. 1 over sigma plus 2 minus 1 over sigma minus 2 minus J3 minus 1 over sigma minus 2 plus J3, where J is simply the square root of -1. Solve. So you should find, like in this case, if you simplify this, it's just a quadratic equation, a second order actually, so it has 2 roots. So you have sigma equals to -7, and another value for sigma is equals to 3. That's what you will find. Sigma is -7, sigma is equals to 3. Good. So because I have obtained sigma as -7 and 1 as -3, I'm looking for the break-in point. That's why sketching the root locus is very important. It's the first thing you do. So I go back because I have -7 and I have 3. So which one is true? Which one is correct? So I come back and see there's sigma as -7. So this point, -7. The other one, is it -3 or 3? Yes, it's 3. So sigma cannot be 3 because this is the point which is 3. So sigma at point 3, it's not the break-in point. The break-in point is on the left half. So it's the negative sign. So therefore, we pick. So the break-in point is sigma equals to -7. Because it can't be the other one. So it can't be this one. It's this one. Because 3 is not where the break-in occurs. Okay? So that is how you pick. So even if this was a third order equation with 3 roots, pick the one that is most appropriate based on your sketch. Because you can clearly see here that we can't pick 3. Break-in does not occur on this side. After all, the root locus we are told is occurring on the left half plane. So that's why we have picked -7. So you have to pick the most appropriate one. Okay, good. Even if you do the differentiation method, dk over d sigma equals to 0, still you're going to get 2 roots because you're differentiating with respect to sigma and then you're equating to 0 and you solve. You're still going to get 2 roots. The same answer. You can try that. Good. So now that is the second part of the question. I don't know what other question there is. So we've done the sketch, we've done the breaking point, the J omega axis crossing. Good. Let's go to the J omega axis crossing. The J omega axis crossing. So this is where we have to use the root table, but even before we get to the root table, we have to get the characteristic polynomial. So that means we have to get the closed loop transfer function. So I'm going to indicate here, we want the J omega axis crossing. At what point do the poles cross the imaginary axis? So we have been told that G of S, the open loop transfer function, is K S plus 2. Again, this is where I expect you to have used your 411 skills. So the transfer function, the closed loop transfer function, should be G of S over 1 plus G of S H of S. Remember, we were told it's a unity feedback system. So solving this, therefore, if you equate, so what is G of S? It's this. So if I solve this, it should be K into S plus 2 over S squared minus 4S plus 13 plus K, of course, into S plus 2. So this is the closed loop transfer function. Closed loop transfer function, which is just T of S, okay? Closed loop transfer function. Remember, this is open loop transfer function, okay? Or what we are calling the feed forward transfer function. Those you did in 4th year. So notice that I need the characteristic equation. So let me make this equation look neat. So therefore, our transfer function, T of S, is K into S plus 2 over, so S squared. Please take note, there is minus 4S plus KS. So I need to put it in order. So that is like plus, notice I want them to be, all of them plus. So I have minus 4S plus KS. So that could be the same as minus 4 into S. I'm collecting like terms, ladies and gentlemen. I'm just collecting, and I have 13 plus 2K. So you have plus 13 plus 2K. So that's the constant term. So basically, I've brought in the points together. So this is what we have as our transfer function. So for J omega axis crossing, the first thing, obtain the closed loop transfer function. Then you see how I have brought the like terms together. I've factorized out the terms together. Then once I have that, then now I can use the characteristic polynomial, or this equation down here. It is the characteristic polynomial. So this is what I use in my root table. Okay. So let's draw the root table. Let's draw the root table. So the highest power I have here, this one is an easy one. The highest power is 2. So we have S to power 2, then S to power 1, then S to power 0. I know by now you should know how to draw the root table. So how do we put in the elements? We have the coefficient of S to power 2, which is 1. Then I skip the next one, then go to the other one, which will be 13 plus 2K. Okay? And there's nothing thereafter. Then for S to power 1, we have K minus 4 then there's nothing else. So it's 0 actually. There's nothing on the other side. So then how do you solve for s to power 0? Remember, to solve for s to power 0, it would be negative. That's what the rule says. You start with a negative of 0 minus, because I'm cross multiplying, 0 minus, this one is k minus 4, and then 13 plus 2k, okay? 13 plus 2k, and the space is never enough. 13 plus 2k. I'm just doing it on the sides because I can't do it on the table. So we'll be having negative into 0 minus k minus 4, 13 plus 2k, like that. Then you divide by the term that is right above s to power 0, which is k minus 4. So clearly I can see that this negative is going to cancel that negative, this minus, so here we are already having 13 plus 2k. So that's what you solve. You know how to do root table. Please go and do it. If you have forgotten, just go and do it. Otherwise, other examples are in your notes anyway. So here is just 0. There's nothing here. Okay, you can leave it blank or you can put 0. There's no problem, whichever you choose to do, or even a dash. Now, the rule says, first let's get the gain. The rule says only, you can see, we have to determine which row can potentially go to 0 for a positive value of k. Which row? Because we have row, the s to power 2 row, the s to power potentially go to 0. For all the elements in that row can go to 0 for a positive value of k. The first row cannot go to 0 because you already have an element that is 1. So you can't change 1 to 0. Okay? The second row, you can see it can go to 0 for a positive value of k. Because if I made k equals to 4, because that's a positive value, then the row, this goes to 0 and this goes to 0. So, and then for the third row, which is s to power 0, if I make k the smallest value of k, remember k varies from 0 to infinity. So the smallest value of k is 0. If I put k equals to 0 here, then I'll find 13. So this row cannot go to 0. I hope that is clear. Let me repeat. For us to obtain the gain in the root table, for you to obtain the gain, you have to look for the row where all the elements can go to 0 for a positive value of k, meaning you can substitute any value between 0 and infinity and the entire row will go to 0. We have just disqualified the first row because you already have a 1 as an entry in that row. So there's no way we can make that 0. So we leave it. We go to the second row. We see that the second row, there's already an element with a 0. So we only have k minus 4. But k can fall between 0 and infinity. So if k was made to be equal to 4, you can clearly see that the entire row will go to 0. Then number 3, you can look at the row and see what value of k can I substitute to make the value, the entire row go to 0. You will find that you substitute any value of k here to make the entire row go to 0. Because the smallest value you can substitute for k is 0. And even if I do that here, the row still doesn't go to 0 because there's already a 13 plus something there. And that row cannot go to 0. Therefore, it is only the s to power 1 row, only the s to power 1 row can yield a row of zeros. Notice you have to justify what you're doing. So I've said only the s to power 1 row can yield a row of zeros. So you pick the elements in that row, meaning you take k minus 4 and you equate it to 0, and therefore k becomes 4. So this becomes your gain at the j omega axis crossing. The point at which the pole is crossing the j omega axis, k would be 4 is 0. Whenever the pole terminates its journey, then the gain is infinity at that point. Remember, the gain varies from 0 to infinity. 0 is at the starting point. Infinity is at the termination or at the ending point. So we have just obtained that k will be increasing, and when it gets to the j omega axis crossing, k becomes equal to 4 at that point. So k at this point equals to 4. And that applies to the other side. Remember, these poles are traveling in a conjugate manner, and they are k equals to 4. The root locus is symmetrical about the imaginary axis. So you can see that k is already equal to, so it means at the starting point, k was 0. By the time they're getting to the imaginary line, k is now 4. K will continue increasing up to the point they terminate, where it will be infinity. Good. So having obtained that, we have to obtain the point, the imaginary axis. For us to obtain the j omega axis crossing, what you have to do, please note, this is the point where we obtained this is the row that gave us the gain. So you have to note the row where you got the gain, then look for the immediate row above the row that you obtained your gain from. But we are looking for an even row, not an odd row. Meaning, and I'll continue repeating this because I don't want any mistakes made by you guys. This is the row, s to power 1 row is the one that gave us the gain. So we have to look, for us to get the j omega crossing, we have to know what is the even row, the immediate even row above the s to power 1 row. And that, of course, there is only one row above s to power 1, and which is s to power 2. And that makes it easy for us. So if, for example, I had s to power 5, s to power 4, s to power 3, s to power 2, s to power 1, s to power 0, and then I obtained, let's say, it is this row. Let's say this is the row that gives us the gain. I'm just using arbitrary. So let's say this is the row that gave us gain. The row that gives you the imaginary crossing is the immediate even row above the row that gave you the gain. So this row gives us the gain. The immediate row above it is an odd row. So we ignore it. We use the even row. So it will be s to power 4 is the one that needs to give us the j omega axis crossing. The reasoning behind that is very simple. Because the j omega axis crossing is a 2-point crossing, it has to be up and down, plus and minus. So you need at least 2 roots. You see, if we use an odd number, this is going to give us 3 roots. Now, 3 roots, it would be difficult for us to decide which one do we take. Okay? But an even number of roots is easy to, because if we have, for example, if you had 2 roots, then you have 2 points. Here we are going to have 4 points, but they are all conjugate. They are all conjugate. So it's easy to take whichever one that is applicable. But if you have 3 roots or 1 root, how are you going to determine which one is the j omega axis crossing? So we need an even number of roots, not an odd number of roots. That's why we are saying you have to look for an even polynomial above the one that gave you the gain. That is very, very critical. So in our case, let's go back to our case. We have obtained the gain at the s to power 1 row. The only row above it is s to power 2. So we have to write out the polynomial in full and equate it to 0, making taking into consideration that our gain K is already given as 4. Okay, so let's come back and say, what is how can you write out this polynomial in row 1 in full? That is very easy. We know S is the coefficient of S squared, so you will have S squared. Then this one is the coefficient of S to power 0, because we have to skip S to power 1. So plus 13 plus 2K. We know this is the coefficient of S to power 0, but you know S to power 0 is 1, so I don't have to write it like that. Okay, should be equal to 0. But K is 4, so we have to write this again as S squared plus 4 is what? 4, that's 8, so I think 21 should be equal to 0. So notice the significance of having an even number of roots, because now we are going to have S squared is equals to minus 21. Therefore, S squared should be the root of minus 21. For those who know their maths, the root of minus 1 is given as J. Okay? So therefore, we can say that S squared. Yes? Please mute your microphone.
Is it S squared or S?
Unless you have a question, you can ask.
Is it S? Because you already have the root on the other side.
Oh, thank you. Thank you. Thank you so much. All right. Yeah. Thank you for noting that. So S, not S squared, sorry, because you already have a root. So S equals to the root of minus 21. So which we can say is the same as, because the root can be positive or negative. Like if I say, what is the root of 4? It can either be plus or minus 2. It's still the same thing. So, but again, we have a negative number here. So it can be plus or minus J, the root of 21. And what is the root of 21? The root of 21 is, let me have my calculator here. So the root of 21, I think 4.6. 4.6, just one decimal place, because it doesn't make sense to have 2 decimal places. There's no way you can plot 2 decimal places on a Cartesian plane or on an S plane. So 1 decimal place is what makes sense. So you can see that the root locus occurs here at 4.6, positive 4.6 and minus 4.6. So this point here is J 4.6, and down here is J minus 4.6. So again, if you plotted your MATLAB and you put in the cursor there, you'll see that that point is minus 4.6 and up there is plus 4.6, whatever it is. Okay, that's why MATLAB will help you check your calculations, whether they are correct or not. So this becomes our J omega axis crossing. Very important. Notice we are taking a lot of time in solving this because we are explaining our way through the solution. But if you already knew what to do, you'd quickly do this stuff very fast and obtain your 20 marks. Okay? It would be very, very easy to do that on your own. But now we have to keep going back, repeating and explaining other concepts just so we understand each other. All right, so I think that makes the solves the problem. So we've done that. So the other question is, find the angles of departure from complex poles. So they want the angles of departure. So let me declutter my diagram here so that these things can be clearer. So the angle of departure, we are trying to look for this point here. This is the real axis. Né? So we are looking for that angle, call it theta 1. We are looking for the angle at which the pole departs, you know, because it doesn't depart at a 90 degrees or it doesn't depart at 180 degrees. It departs at an angle that we are calling theta 1. So let's use this pole as the test point. So you have to draw a line from this pole to all the other points on the root locus. We only have 3 other points on the root locus. One is to the other conjugate pole. The other one is to the 0. Remember, we are only drawing it using the one pole as the test point. That angle that we obtain is the same angle at which the other pole also departs. It's only that it's in the opposite direction. So you don't calculate for both. You only calculate for one. So let's say this pole departs at theta 1. So we draw an angle for the other, to the other pole and also to the other 0. So we need this angle also because it's from all angles are measured from the real axis. So let's call this angle theta 2. So the angle there is going to be theta 2. Let me call it theta 3 because theta 2 would be this one also. This is theta 2. Theta 2. Okay, so theta 1 is the angle for the first pole, theta 2 is second pole, and theta 3 is for the 0. Okay, now please note, I know it looks, it's not very tidy. So what I can do here, I can make it look easy. I'm not going to draw the root locus now. I'm simply going to draw the location of the pole. So there's a pole, a 0 there, and that 0 is at -2, and then this point is 2. So you have a pole here and you have a pole here. And I'm saying what we have to do is to draw an angle from this pole to the 0, and you have to draw another angle like that. Okay? And because we are interested in these points here, okay? We are interested in this angle here. Okay, and we are also interested in this angle here and this angle here. So this is what we are calling theta 1. This is theta 2, and this is theta 3. So if we had another 0, maybe somewhere here, you'd again draw another one there and call it theta 4, whichever it is, but we don't have that. So we only have these 3. So remember again, all pole angles subtracted, all 0 angles added. They all sum up to 180 degrees or an odd multiple of 180 degrees. But the minimum angle is 180 degrees. Why? Because all these points occur on the root locus. You can see that in our case here, all the points are part of the root locus. So if you sum up, we always say that if you sum up all the pole and 0 angles in your root locus, even if there were a million of them, they should add up to 180 degrees or an odd multiple of 100 looking for, and it is a pole. So we have minus theta 1 because it's a pole. Theta 2 is also a pole. So minus theta 2. Theta 3 is a 0, so we add plus theta 3 should be equal to 180 degrees. So we don't know what theta 1 is. Subtract theta 2 to theta 1, that means we are going to have 90 degrees. You can see it's 90 degrees because they're on the same, they're conjugate, they're on the same line. Plus theta 3. So theta 3, you can see, going upwards is 3 on the horizontal, the opposite, the adjacent. The adjacent is, this point is 0. The adjacent is 4. Should be equal to 180 degrees. So theta 1 should be equal to minus 90 degrees plus, what is the inverse tangent of 3/4? Somebody please, inverse tangent of 3/4. Inverse tangent of 3/4. Inverse tangent of 36.9. 36, thank you, 36.9 degrees. So minus this, minus 180 degrees. Because I've taken theta 1 on the other side and brought 180 on this other side. So if you sum this up, that is already minus 270 plus 36. So you have minus 233.1 degrees. Meaning, minus simply means you're looking at the angle in the counterclockwise, I mean in the clockwise direction. So minus 233 simply means it's this, you're giving that angle. But so if you give me that angle, it's the same as saying, which is the same as 126.9 degrees, because 126 means we are now actually measuring in the counterclockwise direction. But if you say minus 233, it's like you're doing it in the clockwise direction, which is still the same angle. So whichever value you obtain here, the answer is correct. But then your most accurate, most preferred answer is this, because we had said all angles are being measured counterclockwise from the real axis. But these two angles are logically or mathematically the same. So I can't fault you for that. Okay. So that means that this is the angle that we have for departure for the complex, from the complex poles. Okay. That is the solution that you need to obtain. And then lastly, we have been asked for the range of gain K. Yes.
Yeah. In the previous sketch, the angle of departure it was departing towards the breaking point. But in this sketch, so my question is it departing towards the zero or towards the breaking point as per the previous sketch?
No, you see, when we say departing, we are not saying that we are departing to zero or to a breaking point. We are actually departing from the pole. You see, it can depart, and then we know that it is still moving on the on the root locus. But we cannot say that it is. We know that all poles must depart and terminate at a zero, because they are poles. They must terminate at a zero. They can go through a break-in point or whatever, but they must terminate at a zero. So our interest is what is the angle of departure. Where they're going after that is not a problem. Our problem is if this pole is leaving this point here, at what angle does it depart at that point? The pole here, these two complex poles that we have here, they're conjugate. So from this complex pole, what is the angle of departure? So once it departs, we know that it is this angle we are leaving at. You see, it's this angle that it leaves. So, I know what you're asking. Not to the whatever, not to the zero, not to the zero. So please note. Thank you. I think maybe I'm the one who was not very forthright with this point. So let me do that again. This angle, ladies and gentlemen, this line we were drawing here is only for us to obtain the angle, but the angle itself, I'm trying as much as possible to try and draw the angle. The angle itself is based on the root locus. So the root locus was moving like this. I'm just trying to see if I can sketch like that. And this one is also departing like that. So the angle that we are talking about is this angle to the root locus. Okay? But the angle is infinitesimally small. It's this point. So you might actually think it's the straight line from here. That is how we obtain the angle. but the angle is actually on the root locus. So if you had a root locus like that, and this is a pole and this is a pole, so we are looking for, and that's the real axis, we are looking for that angle. Okay, but for us to estimate it, and I think it's also provided for in the notes in detail, to estimate it, we have to draw, you know, that point from the 0. Okay, but the angle we are looking for is this. Okay, the one that the pole leaves, but you see the pole has to stick to the trajectory of the root locus. It does not deviate. So the angle is not really the one that helps it move, that it has to move from the pole and then straight line onto the 0. No, it has to follow. It's going to the 0, yes, but it has to follow the root locus. It has to follow the path. So the first angle onto that path is what we are calling the angle of departure from the complex pole. If there were zeros, there would be the angle of arrival into, our angle of arrival into the complex 0. So it's actually the angle that the pole departs at, but along the trajectory of the root locus. I don't know whether that makes it clear.
Yes, thanks.
Okay, good. Is there any other question? Because I think we need to wind up now. Our time is almost up. Yes, find the range of gain K within which the system is stable. This one you should actually be able to tell me. We notice that the gain begins at K equals to 0, and anything on the right half plane leads to instability. We want all the our poles to be on the left half plane. So the gain at the J omega axis crossing was 4. The gain at the J omega axis crossing was 4. Even the J omega axis crossing in itself is a marginally stable location. So for us, for stability, so this question, for stability, we need K to be greater than 4. Any value greater than 4, because anything beyond 4, we know K is on the left half plane, because even the poles, I mean the zeros, are also on the left half plane. So we need anything greater than 4. If you say equals to, then you are also considering the gain at the imaginary axis, which again is a marginally stable area. But for complete stability, you require K to be greater than 4. So that is the range of gain K within which the system is stable. Because we were not asked whether the range where the system is marginally stable. Actually, the J omega axis stability is the gain at which the system is marginally stable. So anything greater than that is what gives us stability in this case. So for any higher value than 4, because here it was 0, here it is 4. So anything higher than 4 is what gives us the full stability range. So that is the range. When K is greater than 4, we know our pole is on the left half plane. Within the root locus, the pole is on the left half plane, and therefore that is the region of stability. So that is the solution for the last question. It's usually just by observation. Good. So unless there's any question, I think I need to end the class here. I urge you, ladies and gentlemen, please try and solve these examples provided in your notes. They're also well explained over there. They're illustrated there. I've given you a MATLAB code that will also help you to solve for even other transfer functions, and then you will always be able to check whether your solutions are correct or not. That marks the end of our discussion today, up until tomorrow, when I want to introduce another aspect. Yes.
I have a question.
Go ahead.
So my question is how, like for this question, we did not calculate the asymptotes. So I was asking, like, how do you determine when you're going to calculate the asymptote so that you can know the direction along which the zeros, the root locus follows?
Okay. when you're sketching, remember I said you only need asymptotes when you're sketching the root locus. Now, we have determined even from our previous class and the examples we did, the only way you use asymptotes is when you know that your root locus is lying at some point or is heading towards some zeros at infinity. So in the previous cases you saw, we had poles that were on the real axis. Then they break away, but we don't know in what direction are they going to go. So the only way to predict the general direction of the movement of poles towards infinity, or as k tends to infinity, was to draw asymptotes. The reason we didn't draw asymptotes in our case here is very simple, and you can actually see it. We already determined from the poles and zeros, we already said we have two complex poles and we have one finite zero. Notice finite zero, meaning that zero, and in this case, it is the zero itself is on the real axis. So we know that our poles will have to come to the real axis because that is where we have our zero. The other zero is at infinity. If you want to confirm that where is the other zero, we said very, very well, you can do this for all the sketches that you want to do. If you calculate the centroid or the real axis intercept, and then you calculate the angle, okay? So this was the sum of the poles, finite poles, minus sum of zeros over their numbers, okay? Number of poles minus number of zeros. Let's just do that and see what happens. The sum of the poles are, we can sum up the poles. So it was, the poles are at 2 plus J3, and you add 2 minus J3, okay? The zeros are not there, so minus the sum of zeros. Zeros are at minus 2, is it? We have 2 plus J3 was one pole. The other pole was at 2 minus J3. The zero was at subtract. Let me do this properly here. We have 2 plus J3. That was the first pole. Plus 2 minus J3. That's the other pole. Minus the zero. Zero is at minus 2. Okay. Over the number. The number of poles were 2. The number of poles are 2. The number of zeros is 1. What does this give me? The j's will cancel out because j plus j minus J3. So 2 plus 2 is 4. We have 4 minus 2. Please make sure that I'm doing this correctly. So it is 6 over 1. Is it 6 over 1?
Yes.
Okay. So that is the intercept. That means at this point here, that is the intercept. So at 6, at some point there, okay? So we know the intercept. Okay, let us see the angles, because that will tell us how to draw the straight lines. So sigma theta would be 2k plus 1, 180 degrees, over 2 minus 1, which is 1, okay? So when k is 0, we have 180 degrees. When k is equals to 1, would be 3 multiplied by 180. So that would be, is it 540 or something like that? Okay. When k is 2, so you can actually see that this point here, this one would be at 120 by, so this is 180 by 3. This is 180 by 3. This is, see, 180 degrees is on that line. So if the asymptote was at 0.6, 180 degrees is on the real axis, right? 540 degrees is still on the real axis. 180 by 5, that is like 185 times, which is still on the real axis. So clearly, even by a quick calculation of the intercept and the angles, you can see that it is confirming that the pole, the zero real axis, draw an asymptote, because the asymptotes are on the real axis. By virtue of this angle, you can see the angle is saying 180 degrees. The other zero was at infinity, so we knew, it was finite, it was at -2. The other zero at infinity is again confirmed here that it is on the real axis, but at infinity. So that's why we didn't draw the asymptote. So this is what I encourage you to do, because in certain questions, I'll simply ask you to sketch the root locus. So you will decide whether you want to use, whether you need to calculate the asymptotes. The only way to do that is to look at the location port. Where is the location of the poles? Where's the location of the zeros? From there, you can tell if the poles are on the real axis and the zeros are on the imaginary axis, then it means that the poles will have to leave the real axis to go to those zeros in the imaginary axis. So you'll definitely need asymptotes. But in our case, you could see that the poles were really on the imaginary axis, and the zeros where the poles need to terminate, the zeros are on the real axis. So therefore, we were bringing those poles from the imaginary axis back to the real axis. So there's no need for us to draw an asymptote. Asymptotes will only help you for those poles that are leaving the real axis and they're heading towards the imaginary axis. And so you don't know, the imaginary axis is large. It's all this area. So you don't know exactly where. But for our case, the zeros were lying on the real axis. One was at infinity, but still our poles could come back and join into the real axis. But if you are leaving, so if these were poles, but now they need to leave, we don't know to what direction. So the asymptotes will help you. So usually you can quickly obtain the asymptotes and the angles to give you an idea of where the poles and zeros are. Those at infinity. Those at infinity. For cases where you have poles and zeros that are finite, so let's say you have 2 finite poles and 2 finite zeros, there's no need for asymptotes, because those 2 poles will terminate at those 2 zeros and they're all finite. So we only draw asymptotes for poles that are at infinity or for zeros that are at infinity. I hope that is clear.
It is. Thank you.
Good. Ladies and gentlemen, I have another class, so please